Tá bom. Good afternoon, everyone. Welcome back to the computational method on optimization. Today, we will continue studying the last method for unconstrained optimization, which is called the subgradient method. Okay, let's review what we have studied before. A classical method for solving this unconstrained problems, because your variable x belongs to the whole space. We can use the following framework, okay? To get, this should be xk plus 1. To get the next point, you have the initial point and the step size and the direction, okay? So you need to somehow descent direction, which means in the product of decay direction and the gradient is negative, okay? And then after you have your searching direction, you determine the step size alpha. Actually, you can choose like the constant step size, which of course requires the Lipschitz constant, this capital L, okay? Or you can choose, you can use some backtracking which satisfies some inequality. For example, this Armigio line search, okay? You do a backtracking until you find some point. Here, the smallest m's, which this inequality is satisfies, okay? This satisfies. This inequality is also called the sufficient descent condition. Okay, next let's consider about the subgradient method. The problem is when we use this line search, okay, this line search framework, and you choose the step size, you choose the direction as the negative gradient, you already assume your problem is differentiable, which means the f is differentiable in the whole domain or in the whole space, okay, which means this the gradient of f at any point exists, okay? So let's consider problems. If f is convex, okay, but not differentiable, here we consider about the convex case because it's easier and it's a classical case in optimization, and we can get a very beautiful and simple theoretical result, okay? We know that for minimize a convex function, we always can we can get the global minimizer. Local minimizer is global minimizer, okay? But there is a problem which is the gradient may not be exist, okay? Will not be exist. So a natural idea to implement this framework, okay? This line search framework is to find something which can substitute the negative gradient, okay? One natural idea is instead of using the gradient, we can take the subgradient, okay? So we take the negative subgradient here instead of the negative gradient, okay? And we choose some proper step size which can guarantee your convergence result. This is what we call the subgradient method, okay? But pay attention, we didn't call it the subgradient descent method because in the previous classes we call the gradient descent method, but here we do not have the descent between the subgradient method here, okay? Which means this method may not be a descent method in each iteration. Okay, let's review what is a subgradient, okay? If we assume that function f is convex and we say a vector d is a subgradient of function f at point x if this inequality satisfies, okay? This inequality satisfies for any x, okay? For any z, for any z belongs to the whole space, okay? And another definition about the another definition related to the subgradient is called the subdifferential. We know the subgradient is a vector at some of the function f at some point. But this subgradient may not be unique, okay? We call the side of all subgradient of a convex function at some point is a subdifferential, okay? It may not be a singleton. Okay, so this is a geometric interpretation of the subgradient, okay? So we have a convex function here, and you will say at this point x, the function is not smooth, so it's not differentiable. And the subgradient, okay, the subgradient defines a hyperplane which can support the epigraph of this convex function at point x and fx. And the negative subgradient d, the pair of minus d and 1, is just the normal vector of these half spaces, okay, of these half spaces. This we give some example. For example, this function is the absolute value function, okay, and we can see in the left part of this function, which means if x is less than 0, the function is smooth, so it's differentiable. So we can see the subgradient is minus 1. The subgradient equals to the gradient, okay? And when x is greater than 0 at the right side of this part, the function is also differentiable because it's smooth. It's a line, okay? And we see the subgradient equals to 1, which is the gradient or the derivative of this line segment, okay? The only problem happens at the 0, okay? Because it's not differentiable, so there is the gradient at this point does not exist. So we can define the subgradient here. Actually, the subgradient at this point is from minus 1 to 1. Actually, you can define several supporting hyperplanes at this point, okay? I can draw a picture here. So you have the absolute value function, okay? This function is fx equals to the absolute function of f. At this point, you can define several supporting hyperplanes. For example, this one, we can define this h1 and h2, okay? Both of these two hyperplanes supporting the epigraph of this convex function at point 0, okay? And we know the slope of these lines which can support this absolute function is between minus 1 and 1, okay? It's between minus 1 and 1. Another function is here. This is also a convex function, okay, but it's not differentiable, especially at the point minus 1 and 1. So we can see the subgradient is like this, okay? The subgradient is like this. We have some classical result about the subgradient, okay? The first is, if function f is convex, then the subdifferential, which is a set of the subgradient of some function at some point, is non-empty, convex and compact, okay? It's non-empty, convex and compact. You can find the reference here, okay? And another one is, we know the subgradient is also, if you have a convex function, and if your set x is a bounded set, okay, and then the union of the subdifferential of the union of the subdifferential in the bounded set x, capital X, is bounded, okay? This is very important for the convergence analysis in this class, okay? Please remember this proposition 3. It's very useful for us. Okay, next, let's consider a question. As I mentioned before, we call this method subgradient method, not subgradient descent method. The problem is, there are some examples which such that the subgradient is not a descent direction, okay? Let's say this example. We consider this function with two variables, x1 and x2, which equals to the absolute value of x1 plus 2 times of absolute value of x2. And at this point, 1 and 0, we can check this 1 and 2 is a subgradient, but the negative g, which is minus 1 minus 2, is not a descent direction at this point 1, 0, okay? Let's prove it, okay? First, this is a graph to show the negative gradient of this function at point 1, 0, which is minus 1 minus 2, is not a descent direction. In this graph, the blue region is where the function value is less, and the green region where the in which the function value is larger, okay? And we can see the 1, 0 is here. This direction upwards is the gradient 1, 2, okay? And this direction is a minus 1, minus 2 is the negative subgradient. And we can see along this minus subgradient, the function value will increasing because it's towards the green region, okay? If you go along this direction, your function value will increase. And next, let's prove it, okay? Okay, for this function, and we can see the subgradient of the function is the subgradient of absolute value of x1 times the 2 times the subgradient of function 2, okay? And at this point, for the first variable, for the first part, the subgradient is 1, okay? The subgradient is 1. Because this we have already analyzed, okay? I will write it here. Again, this is a function of absolute value. Fx equals to the absolute value of f. And the subgradient of this is, here is a minus 1, okay? Here is 1. So the subgradient is like this. So you have for the first variable, the x is 1, okay? So we take 1 here, and the subgradient is only singleton 1, okay? So that's why we have the subgradient of the first part is 1. But for the second part, your variable is 0. So which means at this point, 0, your subgradient is not a singleton anymore. It's an interval. It's from minus 1 to 1. So, but you need 2 times 2, okay? You have a 2 here, so it's from minus 2 to 2, okay? So the subgradient of this function f at point 1, 0 is 1 times the interval minus 2 to 2, okay? And we can check this 1, 2 belongs to this subdifferential, okay? Oh, I'm sorry. Here, this 1 times this interval is a subdifferential because it's the set of the subgradient. And we can see this vector g, 1, 2 belongs to this side, which this subgradient belongs to this subdifferential, okay? So first we have checked this 1, 2 is exactly a subgradient of function f at point 1, 0. Okay, next, let's consider the direction. We consider not the negative gradient, but the negative subgradient, okay? So it's minus g, which is minus 1 and minus 2. And for any t belongs to 0 and 1, let's check the step size, okay? Here, we want to check, because we use this line search framework, okay? We get the next point of xk plus 1 from xk plus the alpha k dk, okay? And here, we choose dk as the minus subgradient, and the step size is t, okay? So we want to first write the formula of this point, and then check the function value, okay? So you have, this is somehow 1, 0 is xk, and the t is the step size, and the d is the minus g is the direction, okay? And then we can write very easily. It's 1 minus t and minus 2t, okay? Then let's compute at this point, what is the function value at this point, okay? So we have the f of 1, 0 plus t times d is f at the function value at this point, and you can check it very easily because t is greater than 0 and minus 1. So we have the final formula of this function value at this point is 1 plus 3t, okay? And since we already know the function value at 1, 0 at the point xk is 1, and we obtain that at the new point 1, 0 plus td is 1 plus 3t, which is greater than 1 because t is greater than 0. For any t belongs to 0 and 1. So, which means you go along this direction. You go along this direction, d. Which direction? The minus subgradient. For any small step size which belongs to 0 and 1, your function value is 1 plus 3t, as we have already get here. And since t is greater than 0, we know this 1 plus 3t is greater than 1, which is greater than function at 1, 0. So which means this direction is not a descent direction of f at point 1, 0. Okay? Because we know along this direction, you choose any step size between 0 and 1, no matter how small it is, your function value will increase. Okay? So this is corresponding to the result as we mentioned here. Okay? You go, this is a subgradient, and this is a minus subgradient is downwards. Okay? You go downwards, your function value is increasing. Okay? Is increasing. Okay. So this is an example of a convex function, and we get a negative subgradient, but which is not the descent direction. Okay. So let's go to the subgradient method. The subgradient method is to solving optimization problems. Okay. Here we assume f is convex. Okay. The subgradient method is defined like this. Actually, in the last example, we already know it may not be the minus subgradient here. We use the minus subgradient minus gk, okay? Because the gk belongs to the subdifferential of f at point xk. We already know this direction may not be a descent direction, but originally the sequence will converge. Okay, so this is the point here. If we choose some proper step size, finally we can still get the convergence. Okay. But actually we have some strategies which, even if the the direction is not a descent direction, but we can keep the function value is decreasing. The strategy is like this. Okay, in each iteration we check the function value at point xk. Okay, and we compare with all the previous function value. And we take the fk best equals to the minimum of fk, the function value at the current point, and all the previous, the best of the previous. Okay, so if you take this strategy in each iteration, we can make sure the fk best is not increasing. Okay, at least it's not increasing. Okay, so if you use this strategy, at least you can get a sequence fxk which is not increasing. Okay, it's not increasing. And okay, and eventually, actually, if after you choose like, actually, eventually it's like this. Your fk best is the minimum of all the previous function values. Okay, so that's why we see this fk best is always non-increasing. Okay, is always non-increasing. And our convergence analyze will mainly based on the estimation of the sk best minus fx star. Okay, instead of fxk minus fx star. This is a little bit different from the analyze for the gradient descent method. Okay, if you remember what we have learned for the gradient descent, actually our convergence analyze are based on this fxk minus fx star, because in the gradient descent method, in each iteration, your function value is decreasing. Okay, it is decreasing. You do not need to take this fk best, but here we can only assume that your fk best is not increasing. Okay, but fortunately we can still get the convergence of the sequence with some step size. Later you will see. Okay, before we go to the proof, let's see some very classical step size options, okay? First is constant step size. It's very easy, okay? You just choose a constant alpha, which is positive constant, okay, independent of k, which is simple, which is quite simple, okay? You do not need to do back checking or any, you do not need to check any inequality in the iteration, okay? Another is called constant length step, okay? Constant length step. Here we do not choose a constant alpha, but we choose a constant gamma, and the step size is gamma over the gk square, gamma over gk square. This means, I'm sorry. Here you should have the gk here, not the gk square. Let me explain here. Because the subgradient method is defined by xk equals to xk, you have minus gk alpha k, okay? So you have the xk plus 1 minus xk equals to the minus alpha k gk. Okay, we take the norm on both sides. You have this, and then this is the norm of, because we know the step size is positive, so we have alpha k here is times the gk, okay? And if we choose alpha k equals to some constant gamma over the norm of gk, then this becomes to the gamma over gk, norm of gk times gk. So you have the gamma, which means if you choose your step size like this, in each iteration, the distance between 2 points, xk plus 1 and xk, is a constant gamma. Okay, is a constant gamma. So it should not be the gamma over the gk norm square. It should be gk norm without a square. Okay. And the next one is called square summable but non-summable, okay, which is very easy to understand. So the step size, of course, you need to have a non-negative step size, okay, but the square is a summable. The square alpha k is summable, but the alpha k is not summable, okay. This is very important, okay. One example can be like I will write it here. For example, you can choose 1 over k, okay? Because this is non-summable, but this is summable, okay? Of course, you can choose like 1 over, no, this is not a square summable anymore, okay? For example, this one. Okay, and another one is like non-diminishing, non-summable but non-summable diminishing step size, which the step size satisfies like this. Alpha k is greater than 0, it's non-negative, and the limit of alpha k is 0, and it's not summable, okay? So as I mentioned before, you can choose your alpha k is 1 over the square root of k. So you have the alpha k approach 0, and the alpha k is not summable. Okay, is not summable. So there are several classical options of step size for the subgradient method, but not all of them can give you the convergence. Okay, so let's go to the convergence analyze. Before we do the proof, we need some assumptions. Okay, we need some assumptions. First, we assume that the norm of the subgradient is bounded, which means the norm of gk is less than or equals to capital G. Actually, this is not very difficult to satisfy. For example, if f is Lipschitz continuous, okay, this can be satisfied. And also we have already proved that. Did you remember the property 3, we have mentioned before, if you have a bounded site, and in this bounded site, the union of the subdifferential is still bounded, okay? So this is not a strong assumption. And another one is the distance between x1 and x star is less than the capital R, okay? This is trivial. So remember these two assumptions. First is the subgradient is bounded. The second is the distance between x1 and minus the solution is less than the capital R. Okay, first we will get some basic inequalities. Here, we need to be careful. Here, instead of analyzing the function value sequence, we're analyzing the sequence xk or xk plus 1 directly here. So what we do is, we compute the xk plus 1 minus x star square, okay? And by the definition of the subgradient, we can substitute the xk plus 1 by the xk minus alpha k gk. Okay, the first equality, we just use the definition of the subgradient method. And then we expand these square terms. You have two square terms and the middle terms here. Okay, do not forget the function f is the subgradient. Okay, and the gk is the function f is convex, and the gk is a subgradient of function f at point xk. So we use the subgradient here, but do not forget you have the minus here. Okay, so you have this less than equals to minus 2 alpha k times fxk minus f star, okay, which f star is fxk, or fx star, okay. The only thing we used here is a subgradient inequality, okay, and you can check it in the previous definition in the previous slide, okay. Okay, and then we applying this inequality recursively, okay, and then we can get this summation here. Okay, we can get two summations. First summation is about this term, is about this fxk minus fx star. So you have fxi minus f star with a summation. And another summation is related to this step size times the gradient. Okay, the gradient. Okay, and then we use two facts. The first fact is this square term is non-negative, and these terms, as we mentioned in the assumption that this is less than the capital R. Okay, so what we have, we put these summations on the left side, and we eliminate these terms, and we use it. We submit these terms x minus x1 minus x star by R. Okay, by capital R. So we have this. The summation of the function fxi minus x star is less than this square of R and the summation of the subgradient, okay? And we can have, we analyze this, the left summation, the summation is the left side of this inequality. We can have this summation is greater than the summation of the step size times the minimum of this. Okay, the minimum of this is trivial. And the minimum of the fxi minus x star, we can take the minimum of both terms. Okay, of both terms. Actually, your fx star, f star is already fixed. Okay, because this is optimal value. So it's just a minimum of this fi from I to 1, from I from 1 to k, you have the fk best. Okay, so this summation alpha I times the fxi minus x star is greater than the summation of the step size times of this fxk minus f star. Okay, so this inequality together with this inequality, we have this fk best minus x star, which is equals to the minimum of fxi minus f star, is less than or equals to this fraction. Okay, this fraction. How can we get this? You just put this fxk minus xa, substitute here, put it here, substitute this summation by this summation, and divided by the summation of the step size on both sides, and then you get this one, okay? And then you get this one. And okay, and we use another assumption here. As I mentioned, we assume the subgradient is bounded. Okay, the subgradient is bounded. So we have this fraction is less than this fraction. We just substitute the normal G square by the capital G square because we know the subgradient of the is bounded. Okay, so we have this basic inequality here. The fk best minus f star is less than this fraction. Okay, there are something which is fixed in this fraction. The capital R is fixed, constant. G is constant. The only thing we need to determine now, or the only thing we need to analyze now, is the step size. We have two parts of the step size. Okay. Actually, we can write it here. So we have this basic inequality, fk best minus f star is less than the fraction, the r square plus g square summation of alpha I, and 2 times summation of alpha I square. Okay. So the only thing we need to analyze is the summation of step size and the summation of the square of step size. Okay. So we can analyze the different step size as we mentioned previously. Okay. Okay. So we have this one, and first let's analyze the constant step size. Okay, if we choose constant step size alpha k equals to some alpha, okay, to alpha, and we have this one. Okay, we have this one, but unfortunately, even if your k is approaching infinity, okay, if your k is approaching infinity, first we choose alpha k equals to some alpha, okay? So this term becomes r squared, g squared, so this is k times, because it's from k, I equals to 1. I equals to 1 to k, okay? This is k times the alpha, and this part becomes 2 times the k times alpha square. Okay, so when k approaches 0, you will have this part is 0, so you have 2 alpha square and g alpha, which is 2 alpha g. Okay, so here we can see if you choose a constant step size, you can get the gap between fk best and fx star is a constant here, which is greater than 0. Okay, which means it may be small or maybe large. It depends on the step size and the boundary and the capital G. Okay, but you cannot get 0 there. And another one, let's analyze if we use the constant length step. Okay, we choose alpha k equals to some alpha times the over the norm of G. Okay, and this becomes like this. Okay, and similarly, we cannot get the convergence. Okay, even if you take the k approaches 0, sorry, here this should be gamma over the norm of gk. Okay, you still have the gap here, and the basic inequality. So this is a basic inequality, and next let's analyze the square summable but not summable. Okay, here we assume the alpha the square is a summable, but the alpha is not summable. Square is summable, okay, but the arranged one is not summable. So we can have the basic inequality like this, okay? We assume this square summable equals to alpha square, okay? So you have this. And we can say, since the alpha k is not summable, the this summation approaches infinity, okay? Approaching infinity. So the right side of this inequality, this fraction approaches 0, okay? This fraction approaches 0, and then we know the gap between fk best minus x star f star is less than or equals to 0, okay? It's less than or equals to 0. And we know we get the convergence if we take this kind of step size, okay? And okay, let's see a numerical example of this kind of different step size strategies, okay? We want to minimize this function, okay? Maximum of m fan function, okay? Actually, it's piecewise linear, okay? Piecewise linear. We choose n equals to 20 and m. You have 100 term. 100 is this fan functions, okay? And the A and B are generated from the normal distribution. Okay, we start with x1 equals 0, and we have this. Okay, if you choose first, you choose the constant step length, which is alpha k equals to gamma over the gk. Okay, go over the norm of the gk. We can say if you choose this very small one, 0.005, you get somehow a convergence, attendance of convergence, but this convergence is not so good. Okay, you can say at the 3000 iteration, the gap is somehow around the 10 to the power of minus 2. So it's not a very good one. Okay, and then we choose the we choose another step size, okay? We choose another one, and let me see. Okay, I'm sorry. Here, this picture is about the value of fk best minus f star, okay? Fk best minus star. And we can see this gap is decreasing, okay? This gap is decreasing. And here, this is not the fk best. This is fk minus f star, okay? And we can see when you choose not a very small gamma, which here gamma is 0.05, the function value is not decreasing, okay? You can see your curve is not always decreasing. It increases at some step and decreases some step, but averagingly it is decreasing, okay? It's decreasing. Okay, this also explains that the subgradient method may not be a descent method. And okay, here this picture is about the gap of fk best minus f star. Okay, but with the right one is the square summable but non-summable. Okay, not non-summable, which is 1 over k. And the blue one is the non-summable diminishing step size, okay? We can say both of the step size, both of this kind of step size gives you the decreasing function value sequence, okay? And next we will introduce a very special case of the step size, which is called Pauillac step size, okay? Which is Pauillac step size. In this case, we need to assume this fx star is known, okay? We already know the optimal value. Actually, this is not very practical, okay? But it can give you some very interesting theoretical result, okay? Theoretical result. Actually, the motivation of this step size is we can use the somehow like the Taylor expansion, but you do not have the gradient. You use the subgradient you substitute the gradient by the subgradient, okay? So this is a kind of first order approximation, okay? So if we substitute this approximation by substitution, and we solve this inequality, this equation, and then you can get the alpha is exactly equal to this one, this fraction, fxk minus f star, okay, and you have the gk, okay, you have the gk, and of course another motivation is, let's remember we already have this inequality, okay? How do we get this inequality? We get this inequality by expand these square terms, okay? And then you use the subgradient inequality. Actually, if you minimize this part, the right side of this part, with respect to the alpha k, okay, with respect to alpha k, so it's a function with one variable, in one dimension, okay? And then you can also get the Poiseuille step size, okay? Just minimize this part, the right side of this inequality. And then we can substitute, okay, after you got the Poiseuille step size, you can substitute the step size alpha k by this one, okay, by this one, and then you get this inequality, okay, and then you get this inequality, and we make summation from k equals to 1 to k, okay, we make summation from I equals to 1 to k, and we get this summation is less than this one, okay, and this means this is summable, okay, and this is a summable, and if we know the subgradient is bounded, and then we can have this summation is less than this one, and then we have the minimize of this fi minus f star is less than this one, okay, and then we can get the epsilon sub solution, which satisfies. If you want to get the epsilon solution, and then you just need to take k equals to this, the Rg over epsilon square, okay, over epsilon square. Okay, and this is a analyze of the this is a numerical result about the Poiseuille step size, and we can see the black one is the Poiseuille step size, okay, and we can see it performs better than the square summable and the diminishing step size, okay, diminishing step size, and actually we can also consider the subgradient method as a projection method, okay. Let's check it. We want to minimize these problems, okay? We want to minimize these problems, and we have the GK is a subgradient. So this is a subgradient method, okay? And we define F star is a minimum of F, and the set S is the argmin of F, which is a solution set of F. Okay, by the convexity, we have this, okay? We have this inequality. And since the F star is we define the F, X star is the F star, so we have this, okay? We have this inequality. And we can define these half spaces, okay? We can define this half spaces defined by this inequality. And the element is X, okay? And we can check, you can check it very easily that the solution set belongs to the HK. And then we can compute the projection of xk onto these half spaces, okay, onto these half spaces, because we know the projection to a half space, you have the closed formula, okay, and the projection, and we can get the projection is exactly this one, okay, is exactly this one. So then we get, actually this is exactly the subgradient method with Poiseuille step size, okay. So we have, if you choose the Poiseuille step size, and the subgradient method is just the projection of xk to these half spaces. And these half spaces separate your parent point xk and the solution set S. And the set S is define the argmin of the F, which is a solution, okay? So this is, we can say, after this we can say the projection method with the subgradient method with a Poyak step size is a projection method, is a kind of projection method, okay? Okay, because of the time, we stop here. Next class, we will discuss a little bit about the feasibility problems and the subgradient method, because the subgradient method can also be used for solving these convex feasibility problems. And then we will go to the second part of this class, the constraint problems. So we